Hello, I am Alina Soslova and today I'm going to present our work on decentralized multi-robot task allocation with time window and ordering constraints. This is a joint work with my advisor, Puyan Fazli. Multi-robot systems provide robust, flexible, and efficient solutions for tackling real-world applications, such as search and rescue, patrol and monitoring, and distributed service and tasks. The multi-robot task allocation problem involves coordinating a team of robots to accomplish a set of tasks at different locations and times in the environment. In order to complete as many tasks as possible while satisfying their time window and ordering constraints, each robot must be provided with a schedule to complete the maximum number of tasks in a minimum time. The time window constraint specifies the time interval within which a task needs to be performed. For example, suppose a task must be performed between 9 a.m. and 2 p.m. Moreover, by forming teams or coalitions, robots can achieve such tasks more efficiently as a result of their collective abilities. To this end, we propose a distributed constraint optimization formalism, or DCOP, to allocate tasks to a team of robots. Despite the vast literature on DCOP, we are unaware of any work that has extended these models to handle tasks with time window and ordering constraints. The proposed DCOP framework facilitates coalition formation among robots to maximize the task completion rate and frequency while minimizing the average task's execution time. Tasks are given to a set of robots through a precedence graph. The precedence graph is a directed acyclic graph with nodes corresponding to tasks and edges representing the ordering constraints between the tasks. Each task may have one or more predecessor and successor tasks. More precisely, completing a task is possible only if all the predecessor tasks are completed. The precedence graph is divided into layers, such that there is no ordering constraints between tasks in each layer. Hence, each layer contains a set of tasks that can be executed independently. There are different ways to represent a DCOP problem. The vector graph is a bipartite cyclic graph chosen to represent the problem. In the vector graph, the variable node x represents the robots and the function nodes f represent the tasks. An undirected edge between a variable node and a function node indicates that robot is capable of performing the task. An approximate method called maxsum is used to solve the optimization problem, since solving DCOP exactly is NP hard. The maxsum algorithm is an incomplete inference-based method that iteratively performs message passing on the vector graph corresponding to the DCOP. The maxsum algorithm allocates tasks layer by layer until all the tasks in the precedence graph are processed. To maintain a schedule for the tasks, each robot creates a simple temporal network. An STN is a graph in which nodes represent the start time or finish time of the tasks, and edges show the duration of the task or travel time between two tasks. Whenever a new task is assigned to a robot, the robot checks every possible position in its STN and inserts the task in the position that keeps the network consistent and leads to a lower make span. To find a solution and a valid schedule for the STN, all the tasks should be assigned start time and finish time points that fulfill their time window, ordering, and travel constraints. This figure at the bottom shows sample schedule for 4 robots after solving their associated STNs. In order to assess the performance of the algorithms, we define 3 evaluation metrics: task completion rate, task completion frequency, and average task execution time. We empirically evaluated the performance of the proposed DCOP framework against an auction-based approach from the literature called Prioritized Iterated Auction, or PIA, under the 3 metrics. PIA handles both time window and ordering constraints imposed on the tasks, but can only be used in non-coalition scenarios. The results shows that in comparison to PIA, our algorithm completes more tasks in 100% of the settings, increases the task completion rate and task completion frequency by 3.3% and 5.4% respectively, and reduces the task execution time by 37.7% on average. For future work, we plan to extend this work in various directions, such as scalability, heterogeneity, adaptation to dynamic environments, handling uncertainties, robustness to failure, and physical limitations of the robots. Thank you for your attention.